Hey everybody, welcome back to part 2 of the average isotope, the average atomic mass lecture that we started previously. What we're going to be doing is we're going to be going through a couple examples to help you work out the math of these problems now. So what we're going to be doing is one example where I'm going to give you some data and then you are going to need to do the calculation, and then the other one's going to be more of an estimation practice to kind of get you prepared for the different types of things that you're going to see on the AP exam. So here is the example. It says natural samples of copper contain two isotopes, copper 63 and copper 65. Remember that the 63 and the 65 are the average atomic, or are the masses of those isotopes. It says the natural percent abundance of copper 63 is 69.09%. Calculate the average atomic mass of copper. All right, so the equation for calculating your average atomic mass is that your average mass is equal to the mass of your first isotope times its percent abundance divided by 100. And what happens is when we do this, it takes that mass and it weights it relative to how much there is in the sample. So when I get the average, instead of it just being a 50-50 average, what ends up happening is it says, hey, maybe isotope 1, there's a ton of it. So I'm going to weight my mass more heavily towards isotope 1 and maybe not so much towards isotope 2. Because then what we do is we add up the mass of isotope 2 and multiply it by the percent abundance times 100 again. And if you'd have 5 more isotopes, you would repeat this 5 more times. So you repeat this process for every isotope and every abundance. So when we take a look at this particular problem, we have copper 63's abundance is 69.09%. So we know its mass is 63. We know its abundance is 69.09. It doesn't tell us anything about copper 65 as far as its abundance goes. But if you think about it, our two isotopes' percent abundances have to add up to 100%. So if copper 63's abundance is 69.09%, then copper 65's has to be this other thing. So what you just have to do is you have to find the difference between these and solve for your x, and your x should come out to be 30.91%. Okay, so that's the abundance for your copper 65's isotope. Now, you don't need to show me this particular work, but in case you were confused or you're, really rusty on your math, we'll just put that in there. So what I'm going to do to show my mass work is I'm going to take 63 AMUs, which is my average atomic mass for my copper 63. Units are going to be super important, so make sure that you include those. So it's 63 AMUs, and then I'm going to take my percentage, 69.09%, and divide it by 100. And the reason why I want to divide it by 100 is to turn that into a decimal so that I don't get this massive number. Okay, so that's copper 63. And I'm going to add that to copper 65. Its mass is 65 AMUs. And then I am going to multiply that by its percent abundance, 30.91%, and divide that by 100. Now again, like I said, if there were several more isotopes, I would just keep adding them on, but this is a pretty small one, so then we should be good to go. Okay? So you can either put this into your calculator directly like this and add them together, or you can get two individual numbers. It is kind of up to you. And then when you put those into your calculator, you should get 63.32 AMUs. Okay, so that's your average atomic mass for that. Oop, I'm sorry, not 63.33. I can't read. 63.62 AMUs. Hopefully that's better. You're like, lady, you're crazy. Okay, now, if I wanted to make your life a little bit difficult, and I like to challenge you, it's AP chemistry. What I could do is I could give you the 63.62 AMUs, and then I could give you the abundances, and I could not give you this mass here. So I could ask you, I could say, hey, what's the mass of this isotope? And then I could have you, instead of knowing what this is, this could be your X. So just be aware that that's something that you can potentially see. and you might get a number that's not perfectly nice and even, okay? Just a heads up for that. The other type of problem that you sometimes see with average atomic mass is more of a thinking problem. So it's like, hey, do you understand the concept of this? So here's our second example. It says chlorine has an average atomic mass of 35.45 AMUs. It has two known isotopes, chlorine 35 and chlorine 37. What is the rough percentage of each isotope? So if we think about this, an average atomic mass is 35.45. And I have two isotopes, 35 and 37. So just the way that my brain works, I'm going to write down 35 and 37. So if you think about, those are our two isotopes mass. The midpoint is 36. So when we think about average atomic mass, because it's a weighted average, if the two isotopes abundances were perfectly equal, we could just do an average of 35 plus 36, and if we divide that by 2, or I'm sorry, 35 plus 37, and if we divide that by 2, we get 36. So 36 here, this number in between, this is not an isotope of chlorine that exists, but if we had exactly 50% of each, our average atomic mass would be 36, okay? Hopefully that makes sense. So what happens is anything that's not exactly 36 is favored one direction or the other. And so we know our average atomic mass is actually 35.45. Okay. This is what we know the average atomic mass to be. So what that means is that if you think about our abundances, our average atomic mass is weighted more heavily towards the more abundant isotope. So in this case, since our average atomic mass is closer to 35, that means that I have more 35 than I do 37, okay? And so if you think about breaking this down, 35.5 is halfway between 36, and 36.5 is halfway between 37. So if you think about it, if 36 is 50% of each, another halfway is approximately, about another 25%, and 35.45 is pretty darn close to 35.5. So what this means is that there is an extra 25% of 35 isotope, and then a fewer 25% of 37. So what that means is my sample is approximately 75% chlorine 35, and then approximately 25% chlorine 37. Okay? So think about it, kind of mentally break that down into what would my average be, and then if it's more towards another element, that means that it's more abundant towards that element's isotope and less so of the other one. Okay? Hopefully this kind of clears things up. If you have any questions, see me in a meet, ask some questions on Classroom, and we'll catch up later.